dissertation defense. And the topic I will be presenting on is democratized wireless networking. Great. Yeah. I think we're good to go. BJ, you can hear me fine?
Yep. Thumbs up.
Okay, sounds good. So, wireless networks and also cellular networks have traditionally been closed off and proprietary and have hardware that is hard to modify and reconfigure. And that means that it's also been very expensive to buy thousands or hundreds of thousands of base stations or radio towers and use them and run spectrum on them. And recently, there have been many technologies that are allowing this to rapidly change and become less centralized than previously. There's different technologies such as open radio access networks, network function virtualization, new radio and commercial off-the-shelf hardware. And all of these things, they make wireless networks more flexible. It makes it easier for different radios to talk to each other and be reconfigured. And it also makes them more accessible to smaller companies and research groups. It lowers their barrier of entry to compete and to innovate. It allows faster adoption of new technologies, and it also allows advancements across network adjacent industries. Despite this, it's not enough. Wireless networks and cellular networks especially are still out of reach for many people. Like I said, having hundreds of thousands of radio towers is extremely expensive, even if you have them and can operate them. To run the radio access network, it is still, the ones that are deployed today are they have limited configuration, even if there's research that's starting to allow it. And then even if you have that set up, spectrum licenses can cost billions or millions of dollars from the FCC, the Federal Communications Commission of the government of the USA, or any other jurisdiction. And then even if you have a license, it requires using locked down radios with very limited configuration. That's very expensive to certify. This stifles innovation. It limits the research contributions and market competition by all but the biggest competitors, the biggest companies. And so this is not very accessible. Thus, we believe that additional network is needed to democratize, meaning to make more accessible, wireless networking to reach its potential as a more mainstream technology that's accessible to organizations and people and research teams of all sizes. Thus, the dissertational statement I have is as follows. Wireless networks can be further democratized via, first, decentralized crowdsourcing of wireless equipment running autonomous mobile networks. Second, short-term dynamic spectrum subleasing. And third, a flexible and trustworthy spectrum license allocation and management mechanism. To support this statement, we have prepared 3 works that I will go through in this presentation in 3 parts for each of these 3. And I don't have that much time, so I'm going to give kind of abbreviated versions trying to give you the problem, the solution, and key results, but there is a lot more in the papers that we've published for these. We'll start first with DNXG. The full title for DNXG is DNXG, a zero trust decentralized mobile network user plane. And this was presented in 2023. I went to Montreal, Canada, and presented it at an ACM conference related to wireless security. Now, as I mentioned before, wireless networks and cellular networks especially are normally controlled by, or they have traditionally been controlled by large governments or corporations only. And to get an understanding of what a cellular network looks like, I've created this figure. It shows 4 components, and on the left you see something called a user equipment, which is usually just a cell phone or a smartphone. That can be used to connect the user to the internet. But to connect to the internet, it talks to a base station, or such as a radio tower, and a fleet or a group of radio towers spread throughout maybe a county, city, or state or country. That group is known as a RAN, or a radio access network. Now, you go from the UE to the radio access network into the internet, but there is one more part in between them called the core network. And the core network is a set of computer servers that are running various services to make sure a mobile network such as a 5G or LTE network is running. Most of these are control plane operations, such as making sure that your calls and texts work, making sure the initial connection is set up, and doing billing and subscribing, charging. But the user plane data going between your phone and the internet, that is when you request YouTube videos to play or Instagram or anything else like that. That is the actual data that the user is requesting after all the control plane operations are set up. Now, these cellular networks are traditionally centralized. That's why I have that box drawn around those two, meaning it's only operated by one very large company, and most companies are not able to afford or participate in this. There are various new technologies that are allowing this to change that I've already mentioned. There's also regulatory changes, such as CBRS, or the Citizens Broadband Radio Service, is in the USA. It's new public spectrum that it's much less expensive to access, or in some cases, free. Also, the NIST, or National Institute of Science and Technology, has recently highlighted the need for zero trust security. To understand what that means, traditionally, 5G and LTE networks have focused more on security at the network edge. So if we look at that centralized box I've drawn, this security prevents external actors from getting into the network. But if somehow they get in, or something turns malicious, or gets compromised, or just malfunctions inside, the security isn't really focused within the network, and because of that, that can cause a lot more havoc. Zero Trust says that this isn't a good solution, and we need to not have any network edge. Instead, everything inside or outside of the network should be treated as a potential adversary. These technologies and regulatory changes are lowering the mobile network ecosystem barrier to entry. They emphasize heightened intra-network security, and they open the door to decentralized network models. What is decentralization? That is basically, it's a term that means to distribute the trust or the decision-making authority from a single entity that maybe owns a group of distributed nodes, and distribute that into many different entities. So that maybe for a cellular network model example, maybe you have 100 base stations and 100 servers that are each owned by 100 participants, and they each have one vote, and together they can decide to do things and form a network, but they each have full autonomy of their own server. There are benefits of this, such as affordable resource pooling and crowdsourcing, where you don't need to buy all of these yourself. You can have a lot of people work with you, and you can still create some network and potentially have a profit off of it. This also has the benefit of zero trust security, because it's more secure in this way if you can have principles similar to that. But that's also a challenge because it's hard to implement this. Other challenges are you need to have a way to incentivize cooperation among different participants that run these decentralized nodes, because why would they want to work together? What benefit are they getting out? And is there any way they can circumvent and profit without doing their parts? There needs to be some way that you can still get them to work together. The other challenge is that 3GPP, which is the standards body that publishes 5G LTE specifications, it focuses more on protecting the network edge than on uncontrolled internal servers. Despite this, decentralization has still had a lot of impact. People are interested, and there's been various radio access networks that have been released and are deployed in real world scenarios, such as helium and pollen. But importantly, these do not decentralize the 5G core. That's where DNXG comes in. DNXG it transforms a mobile network such as a 5G network to allow its servers in the core, specifically the user plane, to be independently run by different actors that each own and operate their own server. And it allows them to still operate through a cooperative security monitoring framework that encourages them to behave correctly. Even though they could do whatever they want, it encourages them to behave correctly through a reputation tracking process. And this is where each node must issue reputation tests that test the other nodes to make sure they're actually doing their job and transmitting user data to and from the internet. If they don't, they lose reputation, and if they do, they gain reputation. And the results of this reputation are averaged and stored on a blockchain that all the nodes also run. And that can be used to determine if you're a high reputation node, you may want to use that node more because they are reliable. If you're a low reputation node, you may want to avoid them, and they will probably not receive as much traffic, and they may just be rejected or need to be fixed. And this matters to have overall network reputation, because if the whole network is less reliable, then people aren't going to trust it in general. But this helps keep everybody in check, and it keeps the network running self-regulated without a central authority. Some use cases of this are, for example, a military coalition where maybe you have a host nation and an ally nation that are deploying, that are in some place, and they each have hardware and they're doing a tactical mission, but they may not fully trust each other. So DNXG can have zero trust like principles that can help their network so that they can trust each other more. You could also have a decentralized crowdsourced community where maybe you have 100 or 1,000 individuals that each own something, and they're able to work together and share their base stations and servers in order to create a larger useful network and profit off of it. And you can even have centralized single entities that still want to have better zero trust in their systems, and DNXG can help improve and go towards a zero trust system. The architecture of DNXG is shown on the left, where we have 4 decentralized nodes in this example, but you can have a lot more than that. And each decentralized node can be owned and operated by a different participant. There are 4 things that each can run. They may run a base station or radio tower. They will also run a UPF, which means a user plane function. And that is in the core network, it is essentially a router that ensures the messages from a phone or a UE get to the internet and back. There's also a blockchain validator, which is a program that all of the nodes run that will store the contents of the reputation data on the blockchain and replicate them between them so there's a synced database. And finally, they all run a reputation monitor program, which carries out the reputation tests needed for this. And then in addition to the decentralized nodes, there is a centralized core control plane node that handles the other operation. Going into what the reputation system does is on the right of the slide. Each node, decentralized node, is going to, it's required to test other nodes at different times at a certain frequency, and it conducts a reputation test by creating a pseudo UE or a fake UE. It will temporarily stand it up and have the UE connect through a different decentralized node's UPF and see, can my fake UE connect to the internet? If it can, then that node is doing its job, and so it passes. If it can't, it fails. And then the results are shared to the blockchain, which the reason we pick blockchain is because you cannot edit the past results of a blockchain. And also, with a BFT or Byzantine fault-tolerant blockchain, you get the property that up to 1/3 of the nodes can decide to not follow the rules and not submit transactions or try to edit things, and the network is going to stay stable for all of them. And once on the blockchain, these reputation tests can be averaged together to form an average reputation for each node. DNXG protects against 6 threats because zero trust systems can have a lot of different problems that can happen. The first is it protects against a node dropping or modifying network traffic. Second, it protects against false reputation reports, such as lying about the results or lying about who reported them. It also protects against node collusion of working together to try to pass each other's tests and fail everybody else's. And it protects against failing to report reputation or reporting too frequently. It also prevents or protects against abusing the reputation testing credentials. And finally, it makes it difficult to identify traffic from a reputation test and pass that, and then not allow anything else. Here's a simple figure of the 5-step process to conduct a reputation test. In this, there is a tester node, which is doing the testing on a different node, the tested node. And first of all, the tester node needs to get credentials for its temporary or ephemeral UE. And so it's going to ask the control plane node for that and get them back. And then on the 3rd step, it will ask the control plane node's session management function, will you please connect me through the UPF that needs to be tested? The SMF will do that. And then at step 4, presumably the UE is connected to the internet. But to see if it actually is, in step 5, the pseudo UE will check, can I connect to some website over TLS or transport layer security? And if I can, then that is a pass. That means the tested node is doing its job. If not, it's a fail. And I don't have time to get into it, but there is a whole process about picking a verifiably random node set to ensure like which nodes you get to pick are random. It is enforceably random, and you have to do it a certain frequency or your reputation is impacted. Once you have finished a reputation test, you put it into a reputation transaction, which gets put onto the blockchain. And each transaction has a couple of items. The blue part at the bottom has a set of node results that, in this case, node 2 tested 3 different nodes, and each of them passed or failed. It then needs to sign that transaction and also say the timestamp of when it happened, and then it will distribute that to the rest of the nodes, which will then choose to accept or reject it based on if the signature is valid and if it seems correct or not. We implemented DNXG on the University of Utah's Powder network, or Powder platform, which is for wireless research and experimentation. And we did this using software-defined radios that were running open air interface, specifically their 5G core and RAN. And we also relied on the Hyperledger Sawtooth blockchain, which is running practical Byzantine fault tolerance. And we ran this on sets of 40 centralized nodes, 16 or 100 nodes. I'm just going to share a few of the results because I don't have a lot of time. In this first one, this is showing a 12-hour period where we had 16 nodes that were being tested, running each other. They were all running this network, and they were constantly testing each other over 12 hours. And in this case, everybody is doing the right thing. They're operating as they should. And so this shows that during the 16 hours, they all had approximately equal opportunity to be tested. They each got tested about 363 times. And during normal operation, they pass almost everything. 99% of the time, they're going to pass. This next slide shows 2 other examples of when nodes are misbehaving and what happens as a result. We'll look at the left one first. This is still the 16 node experiment for 1 hour this time, but the difference now is node 16, that last one, it is still doing its job, but it's going to lie about its test results of all other nodes it tests for the whole hour. And so in the top graph, you can see there's a few more failures than before. And so that's not great. But the bottom graph, if you pull from the blockchain, you can see all the history. And you can see that over the past hour, node 16 failed everybody. That's pretty easy to detect an anomaly and then therefore reject or block node 16 from the future. The other side is a different test, and now we only have 4 nodes, not 16 nodes. And in this case, on the top graph shows the reputation over an hour of like their average reputation from the blockchain. And so they all start at 0 because we just started it, and they're slowly gaining reputation because they're slowly passing each other's tests. The bottom graph shows a user equipment that we had connected, and we were testing to see how often is it passing, how often can it connect to the internet or not. And we started by choosing node 2 for the UE to be connected. And for the first 13 minutes, it's working. But then node 2 is the one that goes bad in this. Node 2 turns off its UPF. It stops processing traffic. And so at minute 13, we see that we start getting some TLS failures. It stops connecting. And node 2 is then going to jump over to node 4 because that was the next highest reputation. A few minutes later at minute 18, you'll see that node 2 is kind of like bluish line. That begins going down, and that's because now the reputation tests issued from the other nodes have begun to fail, and so it's losing reputation while the others are still doing their job. This also shows one other neat thing where it doesn't have to be reputation loss just from being bad on purpose. You can also have temporarily turn off. So node 4 at minute 28, that temporarily has a little bit of network congestion and instability. It fails a few things, but it stays on. But that's enough to slightly lower its reputation. And the UE decides to jump over to node 3 and just continues. So this shows that when you have issues of stability, malicious or not, the UE is able to continue using the network regardless. In summary, DNXG has taken the advantages of changes that allow decentralized use cases by decentralizing the core network's user plane. And it is meant to emphasize zero trust security principles and offer a more reliable quality of service for the core network in crowdsourced environments. That is my first project. We'll now move on to the second project, which is called SpectraLease, Dynamic Wireless Spectrum Subleasing. Yes.
Stepping as when you're not changing the slides, just stepping out.
Oh, sorry. Is this better? Okay, sorry about that. Yeah.
That may be worse for Ryan. So.
Okay, sorry about that. So SpectraLease was presented last month. I went to London, and it was presented at an IEEE conference related to dynamic spectrum access. So previously we mentioned that mobile network operators such as Verizon or AT&T, they will purchase spectrum licenses from the government. They're often very expensive, but they're partially expensive because they give exclusive frequency transmission rights to those MNOs in a specific region, such as a county. And we can see some examples of how different MNOs have purchased spectrum in the bottom graph. We have 3 counties here: Salt Lake, San Francisco, and Anne Arundel. And within each of these stacked counties, we have 3 MNOs within those. And this shows from public FCC data all of the current spectrum licenses that have been purchased by each of these 3 MNOs, typically through auctions. And this graph kind of shows that there's a large distribution and variation depending on where there are. If we look at, for example, the 2.6 gigahertz mark, if we look at MNO B, the pink one, you can see that in the top 2 counties, they have quite a lot of spectrum that they purchased, but in the bottom county, it's way less. It's almost nothing. Another one we can look at is at 1.2 gigahertz. I have this license percentage, and this is showing the amount of total frequency that each MNO bought relative to the other 2. So in Salt Lake, MNO C has the smallest amount of spectrum it's purchased. But if we go look at Anne Arundel, now MNO C has the largest, now has 41. It's way more than the others. Basically, this is showing that licenses are unevenly distributed across geographic area. And the same is true for time, as these licenses are normally purchased in maybe 10 or 15-year periods. But in reality, you can't really predict how many customers are going to be here. Maybe you'll have a new city come up. Maybe people will move away. Even during the day, there's going to be more people using it during the daytime than the nighttime. And so this static licensing issue causes a mismatch between capacity and demand and results in cases of spectrum overutilization or underutilization for short periods of time. This mismatch can cause spectral inefficiency or low spectrum utilization. There are spectrum sharing systems that intend to improve this, but they have limited use cases. For example, you can share between border locations of countries, but setting up things like that takes orders of years and is very manual. The CBRS public system, it has this dynamic spectrum sharing, which is very neat, but it has no availability guarantees because a federal incumbent such as the Navy can come in and require everybody to turn off their networks at any time. And the same is true for other things such as license shared access and cognitive radio, TV white spaces. And those ones you actually have to detect inactivity before you can start transmitting, making these not great for guarantee required commercial use cases. SpectraLease provides a solution to this. It allows spectrum owners, such as MNOs, to identify areas in their licensed spectrum where they have deployed base stations that are transmitting. They can look at their customer activity and their customer demand, compare it to their capacity, and they can find regions where maybe for a minute or an hour, they don't need to use all that spectrum, or maybe they would like extra spectrum. And they can identify that and automatically sublease that to other MNOs that would be interested or in buying or selling that for a short period of time in a specific location. These are very short. It's often limited to a small area. As you can see on the bottom graphs, we have this kind of lease boundary, and there are 2 MNOs or 2 spectrum participants that are either buying the spectrum, essentially, they're getting a lease for a small period of time, or they're giving it up. The lessor is the one with spectrum underutilization, which doesn't need all their spectrum, and so they are selling they're letting the lessee, the other one, use their spectrum license during that lease period only within that band. So they turn off their base stations or turn them down. Then the lessee is the one that needs more spectrum. And so they get to transmit in the lessor's license area for that period of time. And only within the lease time is this guaranteed, but it is guaranteed in that part. There are some challenges associated with doing this. First of all, the lessor has to identify available spectrum that can be safely leased without impacting the customer's quality of service. You don't want to turn off the base stations if you have customers or turn them down too much. So you have to make sure you only turn it down a little bit. Our solution is the spectrum opportunity algorithm. Second, dynamic spectrum licensing requires some sort of communication network to connect potential lessors and lessees that have supply and demand that could work together. And we have a spectrum marketplace API and data model for that. And third, after matching a lessor and a lessee that have agreed, they need to automatically and correctly execute the lease during the lease period. And we have a spectrum allocator and liaison component that carry out that automatic execution. A little bit more on the motivation for this. There's two things I'll go through. If you look at the top graph first, this is showing we used outdoor powder radios to, for a week, measure commercial cells that have coverage areas covering the U of U campus. And this shows a single cell where the blue dots indicate we detected that this cell was on during this time. No blue dots, it's off. So you can see between the red and the green vertical lines, those are periods between 12 a.m. and 7 a.m. where there was basically no activity detected, meaning this particular cell it didn't need its license at that time. It turned them off probably to save power. The bottom graph shows kind of a different thing. We were seeing if we turn down the amount of bandwidth, if we go from 40 or 50 to 20 megahertz, how is that going to impact the customers connected? And 130 PRBs is close to 50 megahertz. As we go down to 50 PRBs, which is closer to 20 megahertz, we do see that the amount of throughput decreases. So maybe you couldn't handle as many customers. But in some cases, if you barely have any customers anyway, maybe that is okay.
Hey, quick question.
Yes.
So,
This one.
yeah, so the cell that you're monitoring in the top graph, that's a single commercial provider. That's a single tower, right?
Yes.
So where is that tower? I mean, is it on the University of Utah campus?
Or quite near it. The coverage area is close enough that our software-defined radio on campus can pick it up.
Okay. It seems remarkable that there would be nothing between midnight and 7.
Yeah, lots of other ones were still operating.
Right? It's like up all night, she's using the cell phone. Okay, and
yeah, there's a lot of cells that are, there's coverage and capacity cells that are covering larger and smaller areas, and some of them get turned off, but not all of them. Some of them stay on always.
sure, thank you.
Another quick question. Same slide. So why there's the third Friday, there's blue dots past the red line. Why is that?
We don't know exactly why it stayed on for 20 or 30 minutes. At other times it turns off. It's probably some algorithm that turns on and off depending on.
Sorry, I misunderstood the title there. This is just a hard 12 a.m. to 7.
Yeah.
Yeah. But you wouldn't necessarily lease that spectrum because it's still on. This is just showing the dynamo battery.
Or you could lease a small portion of it, but not completely turn off the cell.
The pie is open till what?
Cool. Just a couple use cases of spectral lease. We've been talking about Verizon.
Ryan, can you, for my benefit, repeat the question that was asked? Because I cannot hear what they were asking you.
The question was about why there were blue dots going past what, maybe, for example, Friday, the red line on Friday, and it was just a misunderstanding of what the red line was indicating. So it just turns on and off at maybe not exactly the same time every day. Is that good?
What do the red and the green lines indicate?
The red line indicates 12 a.m. The green line indicates 7 a.m.
Okay. All right. So, okay. So you're just indicating what time, and you're saying between that, this thing is mostly asleep.
Yeah, it just calls to attention times that it was turned off.
Okay. And there was some question about cell tower versus a cell. I didn't quite catch that either.
I was just curious about it was remarkable that this one tower it consistently had no activity, and I was just wondering what the characteristics of it.
Yeah, it's not a tower, right? It's a cell in a tower. So
Yeah.
Yeah, all right.
Okay. So the main use case we've been discussing is between AT&T and Verizon or some other mobile network operator. It could be any of them. There are also, for example, in a city, you may have a lot of sensors, Internet of Things sensors distributed throughout that are collecting data, and they only need to report it once a week. Maybe it's a 5-minute upload or something like that. It doesn't matter when they do it. They could do it at 2 a.m. So you could use this short-term leasing in that case. You could also have smart factories or farms use this, and you could also have drone delivery where maybe you are needing to have wireless access and you can conduct more deliveries when you have more spectrum during these leases and less at other times. And then you can also use it for wireless research, such as at Powder. The design of spectrum leasing, dynamic spectrum leasing, has a life cycle that has 4 pieces. First, you need to identify a lease opportunity. Second, you need to advertise this opportunity to find an interested MNO. Third, you need to negotiate between them until you have a lessor and a lessee but you're happy with a lease agreement. And fourth, you must execute the lease agreement on the base stations of both MNOs. We're going to go into that first step first, which is for identifying lease opportunities. We're going to look from the lessor perspective right now. So we're looking at how can we find underutilized spectrum where we could potentially sell it in a lease to somebody else for a short period of time. And I have on the screen if you look at that top left, we have 5 cells in a hypothetical situation where we're going to look at their customer demand or their number of connected UEs at some point in the past. The large cells each have 20 megahertz and the small cells have 40 megahertz. And you might see some of these have numbers, such as this large cell C1, it says 90/20 here. The 20 indicates the capacity of 20 megahertz. And the 90 indicates that during this past period, there were 90 UEs connected. But we can't directly compare those because a UE isn't like a megahertz. It's not the same thing. So what we do is we create a quality of service metric that says how much megahertz or kilohertz, how many do I need on average for a UE in order for that UE to have a good enough quality of service where they have a decent download rate and it stays consistent. So what do we need? And for example, we can say 1 megahertz equals 1 UE. In reality, we will configure this like crazy, but this is just for simplicity here. If we did the 1 equals 1 here, then for 90 UEs, you would need 90 megahertz, and you only have 20. So in this case, that top left cell is very overutilized. But the bottom 2 have way less UEs connected, so they, as a whole cell, are underutilized. However, we can't stop there. We're going to skip the bottom one for time. The third graph is, I'm zooming in on it. The issue is that, and Eric mentioned this earlier, because that one cell was off, but how can you keep on having connectivity? The reality is that there's a lot of cells with a lot of overlap, and you need to figure out in those areas of cell coverage overlap, what's the average geographical proportion average for each of those areas. So let's look at this. For example, we've got this pentagon kind of in the middle. There's this big left cell and then the right big cell. And maybe for that left cell, that pentagon takes up 10% of its coverage area. But for the right one, that's only a third of the circle. So that's going to be more like 30%, like it's a bigger proportion. What we do is we make the assumption that the number of UEs that are connected are geographically distributed, uniformly distributed throughout a cell. And there's a way around that assumption. We don't always have to do that, but by default we do. If we make that assumption, then we can figure out what's the average amount of UEs in there and also the average amount of frequency that they have. And so for each one of these polygons, we can figure out the average for just that, for all of its overlap cells. But we can't just stop there because you can't turn off part of a cell. You have to turn off the whole thing or reduce the bandwidth of the whole thing. And so we recombine each of these different polygons of overlaps into their original full cells. And we see, are there any of those cells where all of the polygons were underutilized? If all of them are, then we draw those black borders around the ones. And for example, the B3 on the top right, that had maybe 10 megahertz under this 1 megahertz per UE assumption that it could have given up and kept its quality of service guarantees. The non-black overlaps, the non-black highlighted parts, those show where maybe part of the cell was underutilized, but not enough of it, and you'd be harming potentially cells elsewhere. So you shouldn't be trying to sell spectrum from that one. Lastly, we need to combine the individual cells that were underutilized into bigger areas because a lessee probably wants to have more than some single cell area to make it worthwhile for them. And this process is the same for the lessee, but you do overutilization instead of under. Now, after we found a lease opportunity, we want to advertise that. The lessor wants to find a lessee. And so they're going to put that onto a spectrum marketplace, which will list what the options are. And each lease listing is the object that you put on, and that's going to say, what is the frequency range? What is the time range? What time of day and how long? Where is it? And other things like what's the max transmit power. And two MNOs will come together, negotiate on that, and at some point will agree. And when they agree, that lease listing becomes a lease definition where they both sign it. They commit to following the lease during that time. And the lease definition is sent. I'm going to reveal the next part of this figure. It is sent to both MNOs infrastructures. A spectrum liaison, that is an object in the core. It's a service in the core, and that is going to figure out which base stations does this lease affect, which region, and it will send it to the proper region. Maybe it's a specific county or city. And within that region, each MNO has a spectrum allocator, which is a program responsible for, first of all, storing the leases. And it stores them in this spectrum allocation table, so it knows what it is allowed to use at certain times. And then when the lease starts, it will automatically reconfigure each base station by turning them on or off or readjusting their power levels and their frequencies that are being used so that the lease starts and ends and that they're not interfering with each other. For our implementation of Spectrum Lease, we have done this and evaluated it in two pieces. There's first of all the spectrum opportunity algorithm, and we conducted a larger scale test around the U of U campus where we analyzed 50 different commercial cells from several different mobile network operators that have coverage areas covering the U of U campus. And we were able to use this data that we collected to estimate the number of UEs connected and the number of physical resource blocks used throughout the day. And we used that to look for opportunities to lease between them. Second, for our spectrum marketplace architecture, we deployed 2 hypothetical MNOs on 5 powder outdoor base stations. And we did that to measure how does it work before and after the lease? Are they going to interfere with each other, and do they have good performance? So just a few results from the first one. This is kind of a complex graph, but this is showing over a 1-day period, we looked at a bunch of different cells that are in the same coverage area on the U of U campus. And this is from 2 different MNOs, which we're going to label one as a lessor and one as a lessee. And in particular, if you pay attention just to that top red arrow, this is pointing to that little legend that says lessee average for physical resource blocks and the lessor average. The lessee, to remind you, is a MNO that has overutilization. They want more, they don't have enough. And the lessor potentially could give away some of it, or I should say sell some of it. The orange lessee, this is the average of all the cells in this area. And you can see that in the morning, it's low because there's not a lot of people awake. But then in the daytime, it goes really high and then it starts to come down at night. And the lessor, the more maroon one, it also is low and then it goes up and comes down. But the key important part to see is the lessee's average usage of physical resource blocks is always way more than the lessor's. And the exact same thing is true with the lessee for number of UEs connected and lessor's number of UEs connected. And this is comparing apples to apples. this is both looking at a total of 25 megahertz of capacity. So it's not like one has way more than the other. Like it's the same thing. The lessee always have more connected. And this means that if you set your quality of service metric correctly, then throughout the day, there's a point when one of them could be considered overutilized and the other underutilized. This shows an example of that, where on the left, this is looking at the lessor, finding underutilized areas. This is the same spectrum opportunity algorithm, but this is actual base station coverage areas that we estimated and around the U of U campus. And the third figure here shows that during this past period, we found instances where a few different cells could have had 2 megahertz or combined 4 megahertz that could have been not needed based on, I think it was a 300 kilohertz per UE quality of service metric is what we were using here. And then the right figure shows the this same like butterfly shape is in blue again, so it's the same one, but the yellow shows the lessee's counterpart. We don't see the lessee's calculation here, but the lessee at the same time had overutilization of like 2 to 9 megahertz depending on the area. And the green shows the overlap between the lessor and the lessee, where at the same time one was overutilized, the other was underutilized, one was over, one was under, and they could have had a 2 to 4 megahertz lease in this particular instance without impacting the QoS metric. And depending on what you set that QoS metric to, we had instances where I think it was up to 17 megahertz or 15 could be leased between them in simultaneous overlapping areas on the U of U campus. Just quickly go over our second part of the evaluation. We deployed two hypothetical MNOs using powder base stations that were running 5G services. And we have, in the first scenario, MNO is the lessor, A. It's going to give all 40 of its megahertz to MNO B. This is pretty simple. In this case, they have the same throughput on both sides. There's no interference. It's quite straightforward. But in scenario 2, we change it a little bit. Instead of giving all 40 megahertz, MNO A is only going to give 20 megahertz. So MNO A keeps transmitting along with MNO B. They're just a neighboring 20 megahertz. And in this case, the throughput does go down for MNO A, like it loses some, but maybe that's okay depending on the amount of UEs it has. And they don't interfere with each other because they're different frequencies. And finally, in the third one, now we introduce a lease boundary around the bottom 2 base stations. And this is to ensure that the MNOs do not transmit outside of the boundary and cause interference. And that's what we find is when the MNO B starts transmitting as the lessee during the lease, it must attenuate or lower the power of those base stations because they're kind of near the edge. And that further reduces the throughput to some degree, so they can't use it as much, but it still is usable. And we can't connect to it outside of the network. The MNOs are not able to interfere outside because of this check, because of enforcing the maximum transmission power. So in conclusion, our spectrum opportunity algorithm found various instances of simultaneous overlapping spectrum over and underutilization between real cellular MNOs on campus. Our lease deployment architecture was able to automatically execute leases and continue having both provide customer service before and after with minimal impacts. And the next steps would be a larger scale test beyond just the U of U campus with more real customer data to see how this continues, to see where else this could be used. So my third project is Spectra Search, which is hierarchical. Yes.
I thought there was a question in the room. Why don't you take that first?
No, somebody left, but.
Okay. So assuming you can continue work on Spectra lease, what do you think are the aspects that are still underexplored and need deep dives?
Deep dives?
Like, what do you think is future work that still needs to be done as part of Spectra lease?
Yeah, there's a slide at the very end that will talk about this, but in short, we estimated the number of UEs, the number of physical resource blocks based on downlink control information. It would be much better to have completely real data from an actual mobile network operator. And then we also were only looking at the U of U campus. It would be nicer to look at larger, maybe full cities, or counties and see, does this persist in other scenarios as well?
Okay. You talked a little bit about using the spectrum for other use cases like, maybe farming, mining, uplink for of
Drone, yeah.
IoT data, drones, and all that. Can you help me understand how do you marry the needs of spectrum becomes, the people that have the spectrum are putting some of their cells to sleep wherever they think there is no demand, right? How is that going to line up nicely with places where you need some of the spectrum and you can actually turn up these sorts of services and use that spectrum? I find a bit of a
Yeah.
mismatch between availability and demand.
Yeah, I mean, two mobile network operators may have similar. We saw on that one graph that one of them they had the same trend of in the daytime they both had more customers, than the nighttime they had less. So that's why I mentioned other use cases such as the IoT sensor, for example, backups, where you need to do that, but it doesn't matter what time of day you could do it. You could do it at 2 a.m. and it would be just fine. The same
I'm
thing could
saying,
apply to.
but you need availability in the place where that IoT sensor is there, or you're in
Right.
trouble.
You'd have to have somebody that has the license and is able to offer a lease at that time. That's right.
But what I'm trying to tell you is market dynamics, the way MNOs go deploy their cell towers and spectrum is based on where utilization happens. Right? If there is no utilization in a certain place, they're not going to go bid spectrum there and pay money for spectrum that they're not going to actually use. It's top dollar that they're paying for spectrum. So what I'm trying to tell you is there is this mismatch between where you potentially need the spectrum for something like a mining operation where there are very few people and use cases, and availability of spectrum
Yeah.
that you can use opportunistically, like what you're trying to do.
The important part is that Spectra Lease is emphasizing especially short-term leases, because a license lasts maybe 10 or 15 years. Maybe it depends, but it's often order of years. And day to day, or even month to month, your customers may change. And so, yes, there's limited use cases that can take advantage of smaller lease periods. But the license is not going to match all the different changes that happen. It's a very static thing for a long period of time. So limited use cases, but potentially some.
Okay, one last question from me. What assumptions are you making about connectivity and hardware between the lessor and the lessee so that this sort of sharing can actually happen?
Yeah, that's what the marketplace architecture has the lease definition sent to both, and from that point forward, they have the same like object that defines what both have agreed to, the maximum transmit power and timing and all of that, and both can run under that. And they both signed it, so they have something to point to if the other lessor or lessee isn't doing their job. But there isn't they aren't talking to each other during the lease, for example. That is something we considered, where can they interoperate to reduce intercell interference at the boundary. Maybe they can send information from each base station back and forth, but that's something we left for future work.
Okay.
Should I start with the third? Great. So the third work is called SpectraSearch, which is a hierarchical system for dynamic spectrum license enforcement, which has been submitted to a conference for peer review. This paper, or this, I should say, this work directly follows off of Spectra Lease. So we're still talking about spectrum licensing. And in spectrum licensing, we have an issue called the spectrum crunch problem, where most valuable wireless spectrum has already been licensed or reserved, especially in FR1, which is 0 to 6 gigahertz. Now, spectrum sharing systems intends to improve this, but they usually require locked down certified radios to operate. And this, when I say locked down, it means it's hard to reconfigure. It's often limited to a single band, and the certification process for this is very slow by the FCC. It's extremely slow and expensive, and it's very hard to modify it further after the fact. There are software-defined radios, SDRs that allow high spectrum configurability, which in theory is a really good thing. It's more usable. You don't have to keep buying hardware for different things. But as a result, these open SDRs have caused lots of FCC interference violations, where the Federal Communication Commission has to sense them and issue fines because they're causing harmful interference, which messes up the signal of other providers in the area. And this is the best they can do because they don't have other proper enforcement mechanisms. The existing enforcement mechanisms are either locking down the radios, which is an ex ante before transmission option, or you can try to sense them after the fact and stop them and stop it as soon as possible. But that's an unscalable and manual effort for the most part. There are concerns about this. The Department of Defense, for example, is potentially considering releasing more spectrum bands, kind of like CBRS. There's one called Embers, which could be shared, but there's been a feasibility report of Embers, and they're not sure if they want to do it. And one of the reasons is that they're worried about the high possibility that non-federal users are not going to follow the rules of the system, that they might transmit and interfere with federal systems, and so they don't necessarily want to. They're concerned. The second one shows a spectrum sharing book, that in this book they said that the reconfigurability of software-defined radios not only makes them vulnerable to unauthorized modifications, it also makes it difficult to enforce spectrum policies. And finally, our own work, SpectRelease, the largest criticism that we got from the reviewers in our when it was accepted to DISPAN was that SpectRelease needs to address the possibility of malicious lessors and lessees, and that without some level of assurance, the spectrum owners may be unlikely to participate. So for these reasons, we have introduced SpectraCert, which is a system that applies public key infrastructure into spectrum licensing. And it allows, it addresses the license enforcement problem, enabling safe, robust, identity-based spectrum sharing. SpectraCert system consists of several components. There's first of all, the SAE, or a spectrum authorized entity. And this represents a government, for example. It could be a company, or it could be just a radio by itself, but it's some entity that owns spectrum, or maybe it owns a license to use spectrum. There is also a SpectraCert, which is a certificate of authorization from one SAE to a different spectrum authorized entity that grants the child SAE spectrum rights to use the spectrum under specific restricted conditions. In this top example, we can see the government has ultimate authority in a particular jurisdiction in a particular area. It gives itself a root SpectraCert with ultimate authority of all frequencies, and then it will issue child SpectraCerts to certain companies that restrict which frequencies are allowed and other things. And eventually that company will send a SpectraCert to a radio. The reason we send it to a radio is each radio has something called a TM, or a trusted module in it. And the trusted module, when it gets a SpectraCert, it will verify the SpectraCert to ensure it came from a proper source, such as the government. It ensures that the conditions were correct. The company didn't try to increase the amount of spectrum allowed from its parent SpectraCert, and it ensures it's still valid, it hasn't been revoked, for example. Only verified SpectraCerts, the TM will only allow the radio to transmit if it has verified a SpectraCert, and only within the bounds of that SpectraCert. The benefit of this is that governments and manufacturers might be more willing to release new spectrum bands such as Embers and allow more open SDRs as long as the radio powers are checked. And this provides the benefit that spectrum rights are protected while simultaneously removing barriers to spectrum sharing, which are often at odds with each other. You can also use SpectraCert to sign and verify attestations made by MNOs, such as submitting a spectrum occupancy report or an interference violation report to know that that MNO had the authorization to use that. And we can tell by verifying the attestation with our SpectraCert.
Actually, can I?
Yes.
One minor. So from reading the dissertation, this chapter, I was under the impression that at least some reports come from the radio, the PM radio SAEs. Is that right, or is that? I mean, you just said that an MNO would make a spectrum occupancy report, right? But presumably this is from data gathered at the PM radios.
Yeah, you could, any SAE could create a report
Yeah.
or something, any piece of data that they want to sign. It could come from a radio to another one. It's not
Okay,
limited.
That's fine, and then this gets to the minor technical issue, that means that the PM radios have to have key pairs. If they're gonna
Yeah.
sign stuff, they have to have,
They do.
okay,
Yep.
thank you.
So the architecture, I have two figures for this, and the first one shows a root SAE or root spectrum authorized entity, maybe the NTIA in the USA government, for example. It creates a root spectrum cert and then issues other spec certs from that root to other spectrum authorized entities. And there may be several levels of SAEs in here, but eventually they're going to want to transmit with a radio. And so you need a final radio designated for the a final spectrum cert designated for the radio that it can use with its TM to verify and then transmit. And importantly, the spectrum authorized entity, it has full control over where, when, and how it can use its spectrum cert to allow other entities to operate. It can choose, and nobody else is ever going to be able to use a less restricted version in their child spectrum certs. This figure shows on the right, this is just another view of the same figure, but this is kind of emphasizing that the top level has more control. They have the most authority, and as you go down levels, you get more restricted. So at the top level, you might have the NTIA, which then gives authority to the FCC or DoD through a spectrum cert for like commercial only or military only. And then as you go lower, you might have a mobile network operator such as Verizon or AT&T. In CBRS, you might have the SAS, which stands for Spectrum Access System. And eventually you might have, for example, subleasing, like SpectraLease, between MNOs. And eventually you'll have a radio and it gets the final spectrum cert, and it's probably very limited compared to what the government could do.
Can I ask another technical question here? This is, all right. So on the last bullet, the radio TM verifies all the spectrum certs. So the thesis mentions that as the spectrum certs go down, some public key is also provided with the spectrum cert, and that. So am I right or am I wrong today?
Yeah, it's
Okay,
you have-
if it's coming up, that's fine.
yeah,
Okay,
we will get to that. That's correct.
Okay.
Yeah. So what are the steps for license transmission on a radio? There is a prerequisite, first of all, which is this 0th step, we can call it, where the TM radio, the trusted module, in order to verify the authenticity of like the origin, the top level spectrum cert, it needs the public key of that government. This is kind of leading into what you're talking about. And so it needs to have that in advance so it can verify that. But then first, let's focus on the company SAE perspective and say that it has this radio. The company wants to transmit with its radio. And so first, it needs to acquire a spectrum cert to become a spectrum authorized entity. So it gets that from, for example, the government. It could be from another SAE token. Second, using that parent spectrum cert, it can create a child spectrum cert which derives from the parent conditions. It's as restricted or more restricted. It can't be less restricted. And it will send that to the TM radio. And it's specifically for that one radio. You can't use the same one for multiple radios. And third, the trusted module in the radio will verify that to ensure the conditions were properly derived, ensure it's active, that it wasn't revoked, and also ensure that it came from a trusted SAE, such as the government, by looking at that public key and verifying the signatures. And only once it's verified can the radio transmit. What does the spectrum cert have in it? There's several components. And first of all, there's the issuer of who is the parent creator, who is this intended for, and then there are multiple types of conditions. The TX, or transmit specific conditions, they say, what are you allowed to do when transmitting? The most important is the frequency range you're allowed to transmit at, but there's also time range, like what time of day. There's the geographic area, so where, maximum transmit power. Maybe you allow or disallow certain brands of hardware, and maybe you allow 5G, but maybe you disallow 5G. You could have more protocol layer restrictions. There are also public key infrastructure specific conditions, such as when is this going to expire? When can you not use it anymore? Maybe you have to check for revocation. You need to check periodically to see if it's been revoked. Maybe you only can, maybe you are not allowed to issue subchild spectrum certs. It's only meant for transmission and nothing else.
So Dan, and now you did the slide.
So-
Go ahead. Can I ask my question and then BJ?
I will repeat your question so BJ can
Okay,
hear.
okay. So this is my question. So we got to where the pub key comes down, right? So the dissertation says that this pub key is provided and presumably it's used to validate the signature, right? But generally you would not trust a pub key that was provided to you in this way, right? Because there's no guarantee that the pub key belongs to the signing authority. You would have to go, you would go look up a trusted certificate authority, right?
Yeah.
Because, you know, the signature and the pub key can be any key value.
Right. Yeah. You can only verify the direct issuer. You can see what they said, but that's why the public key is provided
But
kind
you-
of out of band beforehand to the trusted module.
Previous slide.
I mean,
You had it in the previous.
I understand.
This
Right, you would just consult a different, I mean, I guess the dissertation seems to suggest that the SAEs are not consulting some certificate authority, right? About the identity, I mean, yeah, what is the public key of AT&T, right?
Sure.
I understand that some of them, right? I mean, the root is built into the thing, right? That's how it works, right?
right.
But otherwise, you would generally go off and ask a certificate authority.
Yeah.
Public.
I think you would. And in Spectre Lease, we actually have some of that too. I just had to
Okay.
cut it out for time. But yes, I agree with what you're saying. Yeah.
All right, thanks.
So
Can I
we
ask
just
a
talked-
question?
yes, please.
Can I ask- So, in this thing, you're saying that the SpectraCert has information about max power, geographic area, model, blah, 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 right? That presumably comes from the operator.
Yes, or whoever decides what the rules are for the license.
The person deciding the rules of the license cannot decide what is the hardware that is allowed to use. I mean, that doesn't make much sense to me, but okay.
Are you okay?
But how does somebody know? See, where I'm trying to wrap my head around this, how is this? I mean, how does the trusted module enforce something like this? The trusted module is doing mostly cryptographic functions. These are radio propagation details which it has no notion of, right? How does it validate that you're not somehow violating transmit power?
Yeah, the trusted module is intended to be integrated into a radio. And so I have a slide on this that maybe I can just go to it since we're talking about this. Let me just find the trusted module slide. There would be various levels of trusted modules if we look on the right side, and they would have different risk or price trade-offs, where a low trusted module would maybe be software only. It would not be it wouldn't have as much security checks in it. Maybe it could be circumvented as you're talking about, but it is less expensive. But a high trust level trusted module might require a TPM, a trusted platform module to run, and maybe needs constant revocation checks. And maybe more to your point, VJ, we would design trusted modules to be integrated into the radio, very near the firmware of the radio. And that's actually what we do for our implementation, is it reconfigures the radio according to what is allowed and not allowed. And the idea is, in a more complete non-prototype, this would be a hardened device that would be hard to be able to change, for example, transmit power or frequency bands, because the trusted module itself is preventing it. It's almost like digital rights management to some degree, but not digital,
It's
physical.
like hacking the engine in your car.
Yeah,
Right? You would have to crack this piece of software.
right. Uh-huh.
How do you know? I mean, and it's a similar source.
Yeah. And SIM cards in user equipments, they prevent a user from just going and using whatever they band they want. The MNO kind of controls that. And maybe there's ways you could try to hack it. There's possible things. I think Dustin does some of that, but it's very, very difficult. And the idea would be have a trusted module be kind of similar to that, but for radios, not phones.
So if I can chime in there, Vijay, I think another way to think of this would be when you get your radio FCC certified, instead of saying, oh, you know, this is only going to operate in these bands, it gets certified that this piece of hardware works correctly. Right. So you can totally imagine that becoming part of the certification process. And now you say, oh, I got my FCC certification, I'm good to go. But it's just slightly different way of thinking about it.
No, I get that, Kobus. Where I'm trying to wrap my head around is how does, I mean, the way the way Ryan started off was, the premise was, you want to enforce usage, right? If the configuration, I mean, what I'm trying to wrap my head around is, why is this trusted module any better than, say, just plain configuration that operators or whoever else sets up this SDR today says, oh, this is how I'm configuring this SDR. This is the transmit power for the SDR. You're basically sharing the same information as part of the Spectra set. Why is this better than at enforcement? I'm not following that.
Yeah, I think that the thing here is to say you tie that to a dynamic licensing mechanism. That doesn't exist. Right,
so I'm just worried about the licensing itself, because I can see that you are basically then verifying that from whoever's the authority that has given you the license. What I'm worried about is, at least the way Ryan put it was, he said, oh, we also want to make sure we are not interfering with others and things like that. That's a function of your transmit power, the height, the tilt, all sorts of those things, which tells you where you're trying to transmit it, right? How is that enforced, and why is the trusted module any more trustworthy than the configuration that is being pushed? Because I don't see any checks and balances against that.
Yeah, I think you make a valid point. I mean, I think that functionality to say, am I interfering when I'm using this, that is clearly separate from this functionality, right? This is just saying, oh, I have the permission to use this, and that's the only thing I can do, whatever I've been allowed. But the decision making in terms of saying, oh, well, this is the piece that you can use and that would be okay, that is not part of the story here.
That's fine. I mean, if all we are trying to do is to say, okay, are you allowed to transmit in this spectrum? Okay, I get that, right? But where I was thrown off is all these other details about, the height and the tilt and the power and all of that, which is a very different proposition. And I don't see how you can validate any of that.
Sure. And yeah, like maximum height, that may be something that's more difficult to validate. Some of these things may be enforceable, like the bandwidth and the max power, whereas other ones may be less enforceable. We don't know exactly how these trusted modules are going to be implemented. And some things may just be permission-based, others may be more enforceable. That's that's one of our future work things would be to actually do some more integrations beyond the thing that we have in the valuation and see what else we can include that's more than just enforceable versus informational.
You need to rewind to where you were.
Yeah. Yeah, was there one more, or we?
About that.
Let me get back to were we on this one?
We were.
This one, okay.
Yeah, we were.
I was asking about like for these high trust like TMs, they have to be outside of the world. So, like for example, you have to be able to synchronize your clock in order to understand.
Yes.
So how? I mean, what's the requirement there? Like,
Yeah.
how there's just some kind of like agnostic channel that the TM can communicate across, and the device itself is like responsible for figuring out a way to convey those packets. Otherwise, the TM shuts down.
For sure, like you have to do time clock synchronization in order to do required frequency revocation checks.
Right.
That would
And like this, these CA checks as well, like you need to check certificate chain.
Yeah. You need an online presence for that.
So you're just kind of adding, leave this up to the device itself. It has to provide some kind of like unreliable channel for the TM.
Yeah, for a trusted module that's on this high level of security, it's going to be more expensive to implement, more annoying to operate, but the SAEs that want that level of requirement to ensure that there's no way to circumvent, and that if maybe the federal government, if they're going to have incumbents come in, they want to make sure CBRS already requires you to be online and do this. It's going to be more expensive, yes, but they have that ability to do that. And it would have to be online in that case. Maybe there's less use cases, but they can choose to create a Spectre cert that requires some high level of trusted module that it can only operate with that type, and then it has that requirement.
Kind of wonder, like, are there, I mean, this is really esoteric, but it kind of makes me wonder a little bit if like there aren't like devices out there in the world that like need their SDR to communicate with the outside world. We have like a bit of a chicken and egg problem in the sense that like you might want to do a CA check, but like the TM needs the SDR and kick the outside world in order to make the check.
Yeah.
Like it's kind of pointless because this seems like it would be like much more for things like base stations.
Right.
Other things that actually have some other form of connectivity they're trying to provide access to, but
Right.
I imagine like weird sensors and stuff like scattered around, like having bootstrapping problems because like they need some provisional like SDR allowance.
For sure.
To like bootstrap some more significant certificate.
Yeah. And like CBRS, CBSDs or their base stations have these online requirements, but there may be cases where there's something smaller. One idea that isn't here is the idea that you can have two different Spectre certs issued, and one of them is more permissive, one's less, but the less one doesn't need the SIG checks. The only other thing to mention here is every Spectre cert has the parent certificate chain, which you need to verify that the conditions were properly derived at each step up to a trusted Spectre cert. We have 6 use cases I'll show. There's only 2 on the screen because it's kind of a complex figure of where you could apply Spectre cert to existing spectrum sharing initiatives. It always comes from some jurisdictions such as the government SAE, which might give the FCC a 500 megahertz big chunk of spectrum. And then in the first, this is the most basic use case, is that AT&T or Verizon purchases a auction license and they get that in the form of a Spectre cert, and then they can send that to their radio to transmit. The second use case shows our Spectre lease paper idea, where you may have Verizon got their own and they're going to sublease spectrum and then still use it to transmit as well. Showing 2 more use cases now. The third one is an example of unlicensed spectrum, which does exist, but sometimes there's still a maximum transmit power or something like that. So you could get these Spectre certs very easily because it's unlicensed. Maybe it'll last a long time, but it has certain limits. The fourth shows if CBRS were to use Spectre cert, you would have Spectre certs issued to every SAS or spectrum access system. And then for those that bought priority access license to get higher priority than the general public, maybe they would get a certain Spectre cert and be able to use it too. And we'll go over an evaluation of that later. And then the last 2 are just as simple. If Embers were to be deployed, you could use Spectre cert there. And then in the 6th use case on the right, in Powder, we have Powder uses OpenZMS or Open Zone Management System to manage spectrum for different researchers. And actually, let me just go to the next figure. We actually implemented this last use case in Powder. For our implementation of Spectre cert, we first created a set of APIs, HTTP APIs, that allow these Spectre certs to be created and then sent between SAEs, and also replaced, updated, revoked, and then verified using a prototype trusted module software implementation we have that's paired with an SDR. And we started with that, but then we additionally integrated this with OpenZMS. And specifically, OpenZMS is part of Powder RDZ. And in Powder, the idea is we are allowing researchers to create short-term, maybe 16-hour experiments using certain radios and frequency, and OpenZMS is responsible for allocating those frequency bands at certain times. And we can apply SpectraCert to this by having a different NTIA and FCC and different SAE components that line up to different parts of OpenZMS. And shortly, I'll show you an evaluation of how this works. There's two parts. The second part I just kind of told you about, and was evaluated outside over the U of U campus in a 1 km multi-radio area. We had multiple experiments going at the same time with SpectraCerts. And the first one that we'll talk about before that is a CBRS-like demonstration of the APIs that are sent between SAEs of how you can create, replace, verify, revoke SpectraCerts. And that was done in an indoor setting with several SDRs running open air interface 5G. So looking at that first one, and sorry, it's a little bit small, but I try to make it as big as possible. So this is indoor, and we are calling it a CBRS-like scenario because we're not actually running, like it's not really integrated with CBRS. We don't have actual spectrum access system software, and the NTIA and FCC they're not really involved yet. But we created these pseudo SAEs to represent them. And what's happening here is we have a couple of steps of sending different API requests between these and showing what happens under various scenarios. At first, the NTIA creates a SpectraCert, and it's going to then, let me do this on here so BJ can see my mouse. We create the SpectraCert, and it will send this over to the FCC, which will give a SAS the SpectraCert with the authority to use the 3.55 to 3.7 gigahertz band. And then the SAS is it knows that there are certain priority access spectrum authorized entities. Maybe they purchased in a specific county, they get to use 40 megahertz, which is the max they've allowed by the FCC. And that SAS is going to issue the 40 megahertz to the PAL, which could then use that with its radio, which will verify the SpectraCert all the way up to NTIA to make sure it's correctly derived. And when it does, we see that in the spectrogram on the very right, we start seeing a 40 megahertz band that is being transmitted. We have a separate SDR, which is monitoring for transmissions in this area. So this results in transmissions starting. Now, in the second portion of this is a scenario where our government has said there's a possibility that CBRS as a whole band could be moved somewhere else. And so this is saying, what if that happened? In this case, what if they moved it from 3.55 to 7 down to 3.4? So they moved it down 150 megahertz. In this case, the FCC would revoke the SpectraCert of the 3.55 and issue a replacement lower SpectraCert. And then at each level of the SAE hierarchy thereafter, they need to revoke the old SpectraCerts because they are now out of date, and they can create automatically, mind you, they can create replacement SpectraCerts that still allow transmission. In this case, the SAS decides that it's going to give a different 40 megahertz, 3.42 to 3.46, so it's a little bit lower. And then the radio must stop transmitting, but it can just start transmitting at the lower amount after that. And so we see a change in the spectrogram at that point. Finally, the last scenario shows what happens when we just revoke without replacement. And this is common in CBRS, well, it's actually very rare, but it's possible in CBRS that the Navy or some federal incumbent could come in and require everybody to turn off their transmitters to not interfere. And so if this happens, the SAS has to tell the PAL, you need to stop transmitting, and it's going to revoke the SpectraCert. And when that reaches the radio just, it's revoked, it doesn't work anymore, it stops the transmitter from working. And this whole thing takes like a few milliseconds for each of these API requests. The whole thing takes less than a second to run if you're ignoring the fact of turning on and off radios and government stuff.
Actually,
So,
I have a question here.
Yes.
The metrics. So the fourth metric, OpenZMS, step 6, replacement grant, right? It says it's 5.7 seconds. So I guess I have two questions about this. The first is that 5.7 seconds from when? When does that start?
Yeah.
Is that it?
So these are misleading. These are for the next slide.
Oh,
How about we go to that slide and then you
Okay.
can,
great.
sorry, it's a little. This is what those are applied to, and this is our second outdoor evaluation. And now this is applying SpectraCert into Powder by means of OpenZMS. And so we have the same NTIA and FCC, but now we have different sub-SAEs. And here, in the first step, NTIA is giving a program experimental license to the ability to issue PELs to FCC, and then the FCC gives one to Powder. And that's how it works today. Like Powder has a program experimental license, which is how we can use and transmit with Powder. In step 3, and in this case it's 70 megahertz, it's more than that really, but for this example it's 70. In step 3, the researchers can request to start experiments, which will use parts of that 70 megahertz. And in step 4, one of the researchers decides to do that. They just ask for a little 1 megahertz SpectraCert, and with that, they start a fixed endpoint radio on the hospital, and it's just transmitting a continuous sine waveform. And if you look on the right, it's a little bit hard to see, but there is a thin line that begins and continues through the entire duration, and that's that little tiny transmission that's going the whole time. In step 5, a different researcher at the same time, or shortly thereafter, they want to transmit the 5G base station, and they ask for a 20 megahertz SpectraCert. And they get that, they reserve a radio here, and they're able to start transmitting at a much wider band at that time. And that's on the same time as the other experiment. And then finally, step 6, with step 6, OpenZMS has a feature where it can allow a higher priority user to create a claim which will preempt the initial grant that OpenZMS issued along with the SpectraCert, where it's saying you need to stop using that. But OpenZMS has a different feature where if the experimenter wants to keep researching and keep their experiment going, they're able to not just end the experiment, but they can find a new set of unused spectrum. And that's what OpenZMS does. It finds a higher amount. It will create a replacement SpectraCert at the higher amount. And so we see the transmission shift upward after a little bit of inactivity, and it's able to continue going. Now, as to your point about.
Yeah, so the 5.7 seconds. So when does that start? And when does that
Yes, let me just peek. So the 5.7 was step 6, replacement grant. Yes, so this is just saying how long does it take OpenZMS, the application we integrated it with, how long does it take that when we create the claim within OpenZMS software, how long until that new claim reaches the radio? So that's actually SpectraCert agnostic. That's just the claim comes, the new grant comes with the SpectraCert embedded, and then it's able to act on it.
Okay, so, all right, so my real question when I read this, right?
Yeah.
Is that I was wondering, well, is 5.7 seconds, is that good?
Oh, yeah, I don't know. It's OpenZMS.
Is it?
I'm
just saying, is it?
I'm a little suspicious of this time myself.
Is it?
Be that as it may, it was a quick
Is it
iteration.
acceptable? I mean, is 5.7 seconds acceptable? Because my reading, when I read the dissertation, right, is that this experiment has no authorization to transmit for 6 seconds. Is that right?
It's 6 seconds before they learn of the change in authorization, I believe.
Okay.
But the other thing is that
So there's, okay, so you're saying that there's a potential for conflict for 6 seconds.
the other thing is that it's timestamps taken from OpenZMS. So SpectraCert doesn't actually have any control over this.
Okay,
The-
well, I mean, we can move on. I mean,
Sure.
we can come back to this in a little bit.
Okay.
Myself.
Sure. The SpectraCert itself took just a few milliseconds to verify.
So you should put this in context of CBRS. How long does it take CBRS? What's the requirement on CBRS to?
They have 1 minute. If you have issue a relinquishment request of your grant,
That's
it's
that's
60 seconds.
pretty good.
That's great.
Is it order of magnitude?
Yeah.
Like, keep going.
So
All right.
I had a question along the same
Yes.
notes that I think Eric is getting, right? So in this case, it seems like it's all sort of push based, right? There is no sort of verification coming from the higher authorities or whatever about what is actually happening at the radio level. So what prevents somebody, let's say I'm a malicious actor, I mean, license spectrums are, billions of dollars, spectrum licenses, billions of dollars. What prevents me from getting an initial one, getting this transmission going, and any subsequent change, I just ignore it? How is that enforced?
Sure. The SpectraCert can require one of the PKI conditions is that you may have to have a revocation frequency check. And then that would require the trusted module to be online every so often and make sure that there hasn't been a revocation. Because you're right, the revocations are currently push-based. We actually have APIs both directions. And so you can push a revocation, and I guess they could choose to ignore it. But if you require your SpectraCert to do this, if you require the SpectraCert to check using the TM to do it's asking the higher level, then you can get around that issue still.
I mean, so it looks like you're really trusting your trusted module to do the right thing, which is interesting because your first part of your presentation was zero trust, right? And so you've gone from zero trust to super trust on trusted module.
Zero trust principles. It's not, we don't fully commit to that on DNXG, but yes. Was there anything else, BJ, or I'm basically finished now. So, in conclusion, for SpectraCert, we developed a structure that allows specifying transmission rules and conditions and allows deriving new child SpectraCerts. We also have protocols with APIs that allow SAEs to talk to each other and send these SpectraCerts and then verify in the trusted module whether they were accurate and then start transmitting. And we implemented and evaluated a prototype of this on Powder and also with an additional integration with OpenZMS. And this concludes my dissertation. This is the dissertation statement again, was that wireless networks can be further democratized via a few things, wireless equipment in dynamic spectrum subleasing, and also in spectrum license allocation and management. And our three works are each addressing each point of this dissertation. Well, just a little bit of future work. For DNXG, the next step would be decentralizing other parts of the network, because we only did the core user plane, so you could do control plane functions. We may also be able to integrate with the decentralized RANs like Helium that exist. For SpectraLease, we would want to conduct larger commercial field trial tests, as we already talked about. And for SpectraCert, the next step is really this trusted module we've been talking about, how to integrate that more fully with the radios, and how do we have a certification process for that so that we can ensure that it's going to operate the way we're saying it's operating on. And yeah, that is my dissertation defense. Thank you.
All right, we ran a little long, but let's get audience members that have questions go before we ask the committee.
Go for it.
I want to understand the scope of negotiation with SpectraLease. Like, for example, BJ brought up a point, right? That let's say you give a lease, but then you realize that the tilt is different, and maybe it's causing interference for some reason. So, is there a scope for negotiation when you're given a lease, but you want to maybe change it? I want to understand how
Sure.
What is the term? A leaser.
Lessor,
Right? A lessor. How
took me a couple
lessor,
months to figure those ones out.
how can a lessor probably what use cases and what challenges might there be for such a negotiation to happen in real time?
Yes. So the idea is during the negotiation process, you'd be looking at your base stations, which could start or stop using, and you'd want to figure out that ahead of time.
Okay.
You could have something where after a lease is agreed on, they come together and decide to do something different instead, but they've each signed the lease agreement, which is saying we're committing to this. And so if it turns out, first of all, they're short term. So if it doesn't go well the first time, they could do it differently, but they committed to like stay in this area, this period. So maybe they have to reduce their transmit power more to stay within that.
Yeah, that's.
Other questions?
More questions?
Go ahead, it's your chance, man.
So, one last question from me.
Yeah.
Was there, I think it was spectral release again, was there any studies for, the effects of adjacent channel interference when you give a lease, let's say you have 40 megahertz bandwidth, you lease out 20 megahertz that's adjacent to yours. There have been studies where, let's say QoE, like throughput and stuff can get impacted due to
Are you
interference.
talking about like GAR bands and stuff?
Yeah, like, maybe enforcing 5 megahertz guard band between two of them.
Yeah, we didn't look into that specifically. It wasn't something that affected the evaluation. I agree that it's something that may come up where in
Right.
reality, you might decide to have a guard band when you're making the agreement. So if you wanted to have that, the lessor can just say, I'm not willing to give up that few megahertz in the middle, and maybe I'll stop transmitting too. So like there's ways around that. It's not something we looked into a lot.
Are there any questions on Zoom, other than BJ, who will get a chance in a second? Any other audience questions, as it were? Any other audience questions in the room? Final call. All right, well, thank you. And then I think at this point, we will excuse the audience members and just have the committee.
Thank you for coming.
Thanks, man.
Thanks, appreciate it. Thanks, Mickey.
We probably stopped the recording here, right?
Yeah, that's fine.